Hi, welcome back to this course on computational thermodynamics and kinetics of materials. Today we will see how to have all these different input data for thermodynamic assessment into a file and what are the further things that we have to consider in order to critically assess this input data to do thermodynamic assessment. Okay, so these are going to be the contents today. Input data, whatever we have seen in the last four classes, they are about generating the input data experimentally. If most of the data is available for a system of our interest, they can be collected from literature. Experiments done and reported in the literature can be collected, and then they have to be critically evaluated. We will see how to do these things. In the data collection part, as we discussed over the last four classes, any data related to Gibbs energy can be collected. Usually, constitutional and thermochemical data are the ones which will be collecting, and all data must be converted to numbers. This is very important. If they are available in the form of graphs, let's say activity versus composition, enthalpy of mixing versus composition, things like this can come in graphical form. They have to be converted to x and y data. There are tools like digitizing the graph into xy form. Many open source softwares are there to do that. You can just find it in internet. And data from original sources are also to be checked. These referring articles, basically articles which refer to various experiments done in the past. Maybe they are compiling multiple data from different sources into, let's say, one diagram and things like that. If that is the case, it is good to go to the original source and check the data for its accuracy again. Right? Then comes critical evaluation of input data. So the next step is going to be statistical curve fitting. Once this critical evaluation is done, okay, that will be difficult if poorly evaluated, contradicting or theoretically unacceptable input data are used. Okay, we will see some of the examples for these things in this class. Okay, so therefore do critical evaluation of input data. This becomes a very important step. What is done here is elimination of bad, contradictory or unreliable data. Expertise is required for this critical evaluation. Basically, a reasonable amount of familiarity with various input data generation methods is needed. We have seen few of them in the last few classes. We have to know the principle and the plus and minus, the sources of errors in all these different experimental techniques. Okay, that is quite important. Accordingly, error or uncertainty ranges can be assigned for each data. This has to be done in the input file that will be generated before assessment. Okay. And making a table of details such as technique used, phases present, purity of the sample, experimental conditions, quantity measured, and its accuracy, etc., will bring clarity. So, such a table is required. Usually, if you see any publication of thermodynamic assessment or thermodynamic modeling of so and so alloy system, things like that, you will see that this sort of table is there. A table of all the experimental data collected will be present there. Okay. This is one example. Critical assessment of input data is done because methods used to generate input data can have significant errors. For example, non-isothermal method, DTA, differential thermal analysis, to get the solidus point. Okay. So let's see, there is an alloy here, percentage of B here, it is selected, and from high temperature it is cooled, and the point at which everything becomes solid, all the entire material becomes solid, that is noted as solidus point. So this orange dot, let's say, is the solidus point. We are calling it as non-equilibrium solidus for a reason. Let's say this is the point we are getting from DTA. The reason is, as we cool, there is a particular cooling rate. So things are definitely not achieving the equilibrium at every temperature. The sample is not reaching equilibrium at every temperature. We are not giving it time to reach equilibrium at every temperature, just like in a isothermal exposure. So here temperature is gradually coming down. Because of this, there will be some inertial effect. So if you study more about DTA, you will know that since there is a cooling rate involved, the temperature at which complete solid will form will be much lower than the actual solidus point. Okay, so that is a problem here. The solidus point is marked while cooling. Okay, how to check whether it is accurate? One method is this: long-term annealing is done just below the measured solidus, and on reheating, melting occurs at a higher temperature than the one measured by cooling in DTA. The point is this. So this orange dot is what we got as solidus point. just below this temperature is chosen and long term heat treatment is done there. So material achieves equilibrium there, and from there it is heated up, okay, with certain heating rate, and there is a temperature at which liquid starts to form. It is supposed to be the orange dot, but it happens at a slightly higher temperature than that. Okay, and still that also cannot be taken as the right solidus point, because just below that point again one more point will be selected. You see here again long term annealing is done just below the newly measured melting temperature, before being heated until melting was just observed. Again the heat treatment is done here and reheated, and when temperature goes up, that is where liquid starts to form, not at that temperature, okay, not at the measured solidus temperature second time. The cycle is repeated until the solidus temperature becomes reproducible, and the temperature is then plotted as the true solidus. Okay, this is what is done in finding out the exact or true solidus point. So it is marked here as equilibrium solidus. So now you can sense, just because DTA has this sort of heating rate and cooling rate, so the measured points will definitely not be accurate. Okay, so that is a concern there. So if one uses DTA data as the solidus point, then the error that is associated with that should be significant, and it should be properly assigned in the POP file, in the input file that we are going to make. Okay. Okay, so this is what is to be done. For better results in DTA, heating and cooling rate near the transformation points can be as low as possible. Okay, you see here, here the energy versus temperature, right? So during cooling, this is how the transformation has happened, and during heating it has happened like this. So you see this transformation, this energy going in or coming out is the energy associated with the transformation, and that is in the opposite direction while heating. It is like this during cooling. It may be endothermic here, exothermic here, or vice versa. What happens is, you can see this transformation here is here. Okay, meaning during heating things are here and here, during cooling they are slightly shifted towards the left. Okay, it means if the heating or cooling rate are lower, then these 2 points can come as close as possible. That can be attempted so that the measured values, the transformation temperatures, can be closer to accurate value. Okay. So this is another problem that can arise. The EDS or EPMA analysis for chemical composition measurement can have problems. The point is, when people do EDS or EPMA, let's say they observe a microstructure like this. There is a matrix phase, the blue one, and some precipitates like this, the orange dots here. Okay, so if this is the image seen at this magnification, these are looking like dots. Okay, if one wants to know the composition of this orange phase, then in this magnification itself, if a point is chosen like this, okay, this plus mark, the middle of that is where the composition will be measured. You can see that it is falling somewhere, but if you see the cross section of it, it's going to look like this. Okay, this is basically at this particular zone, a cross section is seen, orange phase, and below the orange phase, right below that will be this blue phase again. Okay, this orange is like a sphere, so it can look like this. Okay, so this is the matrix phase now, the cross section. When the electron beams interact, they interact with this sort of electron interaction volume. They interact with this sort of interaction volume. So this interaction volume is now somewhere here. It is covering both the orange and blue phase. The reason is this dot is put so approximately that it is collecting data from both the phases. So this is a source of error. What one needs to do is magnify this small zone, okay, or zoom into this region, magnify this region, make it look like this, the matrix phase like this, and the precipitate occupying a significant part of the image, and then clearly put this mark in the middle of it. Okay, this may seem to be a very trivial mistake, but more people tend to do this. So this has to be taken care, and the composition values should come from here. Okay, that is a much better representative of the composition of orange particle. So these are only examples of few of the errors that people make in the collecting experiment or doing the experimental measurement of various things that are required for thermodynamic assessment. All these things can reflect in problems in let's say making phase diagram. So in making phase diagram, we said composition measurement is important to get the timeline information. So here there is a phase diagram, binary phase diagram AB. It's a hypothetical diagram where a lot of errors are there. It may look from outset that it looks like a normal phase diagram, but if you carefully observe, there are multiple problems. Okay, we'll see them one by one. Some of these can occur when you try to make the phase diagram experimentally, so you have to be careful. Let's look at them one by one. First of all, there are multiple single phases. We have to note that this alpha, gamma, delta, epsilon, lambda, then there is a mu, there is a psi, and B2, B1. So beta 2, beta 1, and liquid in the top. These are the single phases. Okay, and between the single phase regions there should be two phase regions. Okay, we'll see that also as an error as it comes among these different errors. Let's see one by one. If you focus on this number 1 here, you see two lines. This is a two phase region, right? Alpha and liquid both exist here. This two phase region should end in a single point. It cannot end in a range like this, because this is a pure element A. It will have a single melting point, not a range of melting point. Therefore, this is an error. These 2 points, these 2 lines should converge at a point. That's the error here, number 1. Number 2, here, this is a eutectic reaction, and these 2 lines, this liquidus and this liquidus should join at a point. Now it is not joining in a point. So this is an error here. Number 3 is this information, timeline information of these 3-phase equilibria, okay, or eutectic reaction compositions. This line cannot extend beyond this point. So there is a problem here. Number 4 is an interesting problem where the boundary of this alpha phase is like this here and like this here, and at this particular temperature here, at this particular temperature, what is the composition of alpha? Is it this point or this point? Both are indicated, so that is a mistake here. So this is an error in constructing phase diagram. This line should come and join here, or these 2 lines should meet at a point, not like this. That is this error 4. Error 5 is a little difficult to understand without the Gibbs energy composition diagrams. What it says is this: the extrapolated line from here is going into alpha region, not this two phase region. Alpha plus delta region is here. Okay, this extrapolated line of this boundary should go into that two phase region, not away from that. This can be understood only when we construct Gibbs energy composition plots. And here also this boundary should get extended into this two phase region. This is a two phase region between alpha and gamma. This is where this dotted line should come into this region, not away from this into this alpha region. Okay, this is an error. That is 5. 6 is this solvers line here cannot end somewhere here randomly. If it ends like that, it means that there is a two phase region here. Single element having two phases is not possible. Okay, and if there is a allotropic transformation, here one phase, here one phase, then it is possible. Now it is not correct. Okay, then 7, you can already see this is a 7 is the invariant line here. There is alpha phase in the left side, delta phase in the right side. These two phases combine to give a new phase gamma. This is a peritectoid reaction, but this point should be touching here, only then this is correct. Okay, that is error 7. Error 8 is even more severe because it says there is a reaction with the horizontal line. Gamma, delta are the two phases on both sides, and there is no product or there is no parent. Okay, there should be 3 phases actually. In any invariant reaction in a binary, there should be 3 phases, but only 2 phases are marked in 2 sides, nothing above or below. So that is a problem here in point 8. Point 9 is a very important problem. Epsilon phase is there. This is the single phase field of epsilon. Okay, and delta phase field, this is also a single phase field. Between two single phase fields, a two phase field should come. Okay, You see here, alpha liquid is there. This is a two-phase field. Alpha and gamma are there. Between that, there is a two-phase field, alpha plus gamma. So that here delta and epsilon, in between there should be a delta plus epsilon region, and that is not there. That's the error here. So all single phase fields should have a two phase field in between. Only exception is order disordered transformations. If there is a ordered phase at low temperature and becomes disordered phase at higher temperature, then order and disorder phase can have a boundary, and that is a temperature, and that is a transformation point for order to disorder transformation. In copper zinc system in the last class we have seen that. Therefore, this is an error because the two-phase field is missing. And then number 10 is a two-phase region of this sort. Gamma and epsilon two-phase region is here, and this cannot end like this because there is a tangent construction, and the tangent should be horizontal. This should actually meet in this peak point, peak temperature, not here. These two lines should meet here. Okay, that is the error here. And 11 is this sort of structure, two curves like this meeting at the peak temperature is happening here, but the solidus line is not shallow like this, it is a sharp one. So it is like a discontinuous line. So this sharp one also is not permitted. If you plot Gibson-Edgeus's composition plot and get the common tangent, it would not be a horizontal line if this has this kind of geometry. Okay, that is 11. 12 is this minimum here. This kind of minimum can happen only when there is a monotectic reaction horizontal line here. That line is not there. Therefore, this 12 cannot happen like this. And 13 also is a maximum that can happen only when there is a monotectic line or syntectic line that is not there, or at least this sort of two curves are there. One more curve should come like this, and below that there should be a solid congruent line, that is also not there. So let's say this epsilon is like this. Okay, that is also not there here. So this 13 also is a problem. 14 is quite obvious, it's an invariant reaction. There is a phase here liquid, left side epsilon, right side mu, but invariant reaction will happen at only one temperature, not over a range of temperature. This should be a horizontal line. So this is a straightforward error. And 15 is this line being discontinuous, it is absent below this. This is a problem. This may or may not be a problem, provided if experiments are done only up to this and beyond this experiments are not done, people give dotted lines and all, and that is artificial, that is not a feature of the system. Okay, so if that is there, then this is not an error. If the experiments are not done here and that is indicated properly, then this is not an error. Otherwise, if this is given as a feature of the AB system, that is a problem, that is an error, right? That is 15. 16 is where like here sharp line is there in the solidus, here liquidus itself is having the sharp line, so that is error, that cannot be like that. And 17 is an invariant reaction like this, mu is one phase, liquid is the other phase, beta 1 is the third phase. So it's more like a peritectic reaction, but problem is this point is the composition of beta 1 and also the composition of liquid, that's how it looks. Okay, therefore liquid and one solid both cannot have same composition, that is the error here. Okay, right. And 18 is also a very interesting error. If you see, liquidus is going up, solidus is going down compared to this pure metal. Okay, this cannot happen. Either both liquidus and solidus will go up, or liquidus and solidus will go down. Okay, there will be a V like this. The top line will be liquidus, the bottom line will be solidus, or there will be a V like this. Okay, solidus like this and liquidus above that. It will be like this. Okay, not like V of this sort where solidus goes down, liquidus goes up. That cannot happen. Okay, that is 18. 19 is also quite obvious to see, there is a horizontal line, so there is a invariant reaction, there should be three phases involved. Okay, mu, beta 2, epsilon is fine, but beta 1 is also coming here, So if you see beta 1 is giving beta 2 plus mu, like a Tactile reaction, what about this epsilon, this chi phase? So this is a problem. 4 phases are there with a horizontal line. This is not permitted. So this is also an error. 19. T is also an error. If you see, the boundary of this beta 1 is going like this, and boundary of beta 2 is crossing over that. This crossover also is not right. This is another error. Okay. Then 21, 22, 23, these three are showing sudden changes, abrupt changes in these lines. So you see 22 is like this, 23 is also sudden changes in the slope are seen. That is also not permitted. Okay, so these are the different errors that one can see in the phase diagram. So if you are constructing from experimental data phase diagrams, make sure that such errors don't occur. Okay. Okay, there are much more errors compared to this. These are only glimpses of what things can go wrong. So one has to be careful in critically evaluating all this data and then taking it to the input file. So once we will see the structure of input file and all once we go to thermodynamic assessment classes. Okay, so today we'll stop with this. Thank you. I hope the lecture is useful. See you in the next class.